Uncertainty techniques. Supervised learning. Classification. Monte Carlo dropout. Description. Uses dropout during inference to create an ensemble of predictions, providing uncertainty estimates. Advantages. Simple to implement. Integrates with existing neural networks. Disadvantages. May not capture all sources of uncertainty. Computationally expensive. Bayesian neural networks. Description. Incorporates Bayesian inference to estimate the distribution over weights, providing uncertainty in predictions. Advantages. Provides principled uncertainty estimates. Disadvantages. Complex to implement. Computationally intensive. Ensemble methods. Description. Combines predictions from multiple models to estimate uncertainty through variance in predictions. Advantages. Robust and generally improves predictive performance. Disadvantages. Requires training multiple models. Resource intensive. Bootstrap aggregating. Description. Generates multiple datasets via resampling. Trains models on each. And combines predictions. Advantages. Simple and effective for many types of models. Disadvantages. Computationally expensive. Sensitive to data quality. Quantile regression. Description. Predicts quantiles instead of mean values, providing uncertainty bounds on predictions. Advantages. Provides direct prediction intervals. Disadvantages. Requires appropriate quantile loss functions. May be complex for high-dimensional data. Regression. Quantile regression. Description. Predicts specific quantiles, offering a range of possible outcomes. Advantages. Gives a full picture of potential outcomes. Disadvantages. Can be sensitive to outliers. Computationally expensive for high dimensions. Gaussian processes. Description. Non-parametric models that provide uncertainty by predicting distributions over functions. Advantages. Provides natural uncertainty estimates. Flexible. Disadvantages. Scales poorly with large datasets. Computationally intensive. Bayesian neural networks. Description. Uses Bayesian inference to provide a distribution over model parameters. Advantages. Captures model uncertainty. Suitable for small datasets. Disadvantages. Complex. Computationally intensive. Bootstrap aggregating. Description. Aggregates predictions from models trained on resampled datasets. Advantages. Reduces variance. Improves stability. Disadvantages. Resource intensive. Dependent on data quality. Ensemble methods. Description. Combines multiple models to improve predictions and estimate uncertainty. Advantages. Improves robustness. Handles complex patterns. Disadvantages. Requires significant computational resources. Complex implementation. Unsupervised learning. Clustering. Bootstrap methods. Description. Uses resampling to create multiple clustering solutions. Assessing variability and stability. Advantages. Simple. Improves stability. Disadvantages. Computationally expensive. Sensitive to initial conditions. Consensus clustering. Description. Combines multiple clustering results to identify consensus clusters. Advantages. Enhances robustness. Mitigates outlier effects. Disadvantages. Complex. Requires multiple clustering runs. Bayesian mixture models. Description. Models data as a mixture of distributions, using Bayesian methods to estimate uncertainty. Advantages. Provides probabilistic assignments. Flexible. Disadvantages. Complex. Computationally intensive. Variational inference. Description. Approximates posterior distributions to provide uncertainty estimates in clustering. Advantages: scalable, efficient. Disadvantages: approximation may introduce bias, complex to implement. Dimensionality reduction. Variational autoencoders. Description: uses stochastic variational inference to learn low-dimensional representations, providing uncertainty estimates. Advantages: captures complex relationships, provides uncertainty. Disadvantages: requires tuning, complex. Bayesian PCA. Description: extends PCA with Bayesian inference to estimate uncertainty in components. Advantages: provides uncertainty in dimensionality reduction. Disadvantages: complex, computationally intensive. Probabilistic PCA. Description: models data probabilistically, estimating uncertainty in reduced dimensions. Advantages: provides a probabilistic framework, handles noise. Disadvantages: limited scalability, computationally demanding. Gaussian process latent variable models. Description: combines Gaussian processes with latent variable models to estimate uncertainty in reduced dimensions. Advantages: flexible, captures uncertainty. Disadvantages: complex, not scalable to large datasets. Reinforcement learning. Value-based methods. Bayesian Q-learning. Description: incorporates Bayesian inference in Q-learning to provide uncertainty in value estimates. Advantages: captures uncertainty, improves exploration. Disadvantages: complex, computationally intensive. Thompson sampling. Description: uses posterior sampling to balance exploration and exploitation in uncertain environments. Advantages: efficient, theoretically grounded. Disadvantages: requires prior knowledge, sensitive to model misspecification. Ensemble DQN. Description: uses an ensemble of Q networks to estimate uncertainty and guide exploration. Advantages: improves robustness, captures uncertainty. Disadvantages: resource intensive, complex. Monte Carlo dropout. Description: applies dropout during Q-value estimation to create uncertainty-aware policies. Advantages: simple to implement, integrates with existing networks. Disadvantages: computationally expensive, may not capture all uncertainties. Policy-based methods. Bayesian policy gradient. Description: applies Bayesian inference to policy gradient methods to estimate uncertainty. Advantages: improves exploration, provides principled uncertainty. Disadvantages: complex, computationally intensive, uncertainty penalty. Description: penalizes uncertainty in the reward function to guide exploration. Advantages: simple, effective for risk-sensitive tasks. Disadvantages: may be problem-specific, requires tuning. Thompson sampling. Description: uses posterior sampling to select policies, balancing exploration and exploitation. Advantages: efficient, balances exploration. Disadvantages: requires prior knowledge, sensitive to assumptions. Bootstrapped policy optimization. Description: uses bootstrapping to create multiple policy estimates, capturing uncertainty. Advantages: improves robustness, handles non-stationarity. Disadvantages: resource intensive, complex implementation, anomaly detection, statistical methods, extreme value theory. Description: models the tail behavior of distributions to detect anomalies with uncertainty. Advantages: effective for rare events, provides statistical rigor. Disadvantages: requires large data sets, sensitive to model choice. Bayesian change point detection. Description: detects changes in time series data with Bayesian inference, providing uncertainty estimates. Advantages: handles non-stationary data, captures uncertainty. Disadvantages: complex, computationally intensive, Gaussian process regression. Description: uses Gaussian processes to model data and detect anomalies with uncertainty estimates. Advantages: flexible, captures uncertainty. Disadvantages: scales poorly with data size. Computationally intensive, hidden Markov models. Description: uses probabilistic models to detect anomalies in sequential data, providing uncertainty estimates. Advantages: handles temporal dependencies, provides probabilistic framework. Disadvantages: complex, requires parameter tuning, machine learning methods, autoencoders. Description: uses neural networks to reconstruct data, with high reconstruction error indicating anomalies. Advantages: effective for complex data, captures nonlinear patterns. Disadvantages: requires large training data, sensitive to architecture. Bayesian neural networks. Description: uses Bayesian inference in neural networks to provide uncertainty estimates for anomaly detection. Advantages: principled uncertainty estimates, flexible. Disadvantages: complex, computationally intensive, ensemble methods. Description: combines multiple models to improve anomaly detection and estimate uncertainty. Advantages: robust, handles diverse anomalies. Disadvantages: resource intensive, complex, isolation forest. Description: uses decision trees to isolate anomalies, with fewer splits indicating anomalies. Advantages: efficient, handles high-dimensional data. Disadvantages: assumes anomalies are few and different, sensitive to parameter settings. Time series forecasting. Classical methods. ARIMA with Bootstrap. Description: combines ARIMA modeling with Bootstrap resampling to estimate uncertainty in forecasts. Advantages: well understood, handles time series data. Disadvantages: assumes linearity, computationally intensive, state space models. Description: uses probabilistic models to capture the underlying state of a system and forecast with uncertainty. Advantages: handles non-stationary data, captures uncertainty. Disadvantages: complex, requires parameter estimation. Bayesian structural time series. Description: uses Bayesian methods to model time series data, providing uncertainty estimates. Advantages: flexible, captures structural changes. Disadvantages: computationally intensive, complex, Gaussian processes. Description: models time series data with Gaussian processes to provide uncertainty in forecasts. Advantages: flexible, captures uncertainty. Disadvantages: scales poorly with large data. Computationally intensive. Deep learning methods. Bayesian RNN. Description: uses Bayesian inference in recurrent neural networks to estimate uncertainty in time series. Forecasts. Advantages: handles